In A-level papers, this sort of differential equation with an x and y going on is typically at the end of a paper, and you have to differentiate using separation of variables and so on. But here it's question 2. We're just expected to be able to deal with this kind of thing. We're given that we've got this is a curve, and we don't know exactly what it looks like. I don't know, maybe it's like that. And we're told that a line with equation y equals 2x plus 5 is a tangent to this curve at a point P. So maybe it's here. And this is absolutely crucial because they'll have the same coordinate at P and the same gradient. In fact, not just the same gradient, but it's y equals mx plus c, so the same gradient of 2. And therefore, we can write the following down. X plus 1, sorry, I shouldn't say therefore, I should say at P, x plus 1 times x plus 2 times 2 we equal x times y. But remember I said they have the same coordinates. So this y here is the same as this y here, and we can replace it by 2x plus 5. Essentially, all I've done is replace this by 2, and now I'm solving a pair of simultaneous equations which will involve quadratics. So x times 2x plus 5. Okay, I'm going to bring the 2 here. I'm not going to expand it quite yet. I'm going to expand the quadratic. So I get x squared plus 3x plus 2. Expand this one as well. Now expand this. These two cancel, which is fantastic. I can minus the 5x on both sides and minus the 4. So we're going to get x is minus 4. And I can sub back in to get y. It's going to make sense to sub it back into the most simple one. So it's going to be 2 times minus 4 plus 5, which is going to be minus 3. Therefore, P has coordinates minus 4 and minus 3. Good start. Now on to the main event. We're asked to find the equation of C given our answer in the form y equals f of x. So here's our equation. It's a differential equation. We're going to need to use separation of variables, basically get the y's onto the left-hand side and the x's all onto the right-hand side, because then we can integrate. So sorry, that was part A. Okay, part B. Now I'm going to divide through by y, so it's going to become 1 over y dy by dx equals x over that double bracket x plus 1, x plus 2. Now I can integrate with respect to x. Sometimes I see people kind of multiply through by the dx and then integrate, but technically speaking, we should do the same thing to both sides. It just turns out that when you differentiate this with respect to x, this is dy using the chain rule, and then we're okay. So we've set things up. It's like just like how do we integrate this? And to do that, we're going to have to write it in partial fractions. So that's our starting point. Multiply through. We let x equal minus 2, then this term disappears. We get minus 2 equals minus b, b equals 2. And then x will equal minus 1, minus 1 will equal a. So we're sorted. I'm going to write the b term first, and then the a, because then I can just put the subtraction here. Okay, nice. When we integrate 1 over y, we're going to get ln, technically with a modulus around it. And then here, bring out the 2, and it's going to be ln of x plus 2. Again in the modulus, minus ln x plus 1. Don't forget to add the c. We want to now make y the subject and hence remove the logs. So we've got ln y equals. What we can do is we can use the third rule of logs to make this ln x plus 2 all squared. And then because we are minusing a log, we can in fact divide by it. And we're going to get ln x plus 2 squared over x plus 1, all in modulus signs. And then I'm still adding c. Now instead of adding c, I could actually add, say, ln k. And that in fact allows me to bring that inside the log as well here. So I don't add a constant, I'm multiplying by a constant instead. I should probably just write down that c is equal to ln k. Now we can essentially just undo these logs. If these two things are equal, then we can write down the modulus of y is equal to k times the modulus of x plus 2 squared over x plus 1. I brought the modulus like around the whole thing. That's absolutely fine because it's, this is positive, this is positive. It doesn't matter, here what's going on. Equivalently, if you don't like that, you can imagine raising both sides to the power e, and then these cancel, and you get the same thing. Now, I've got modulus signs in there, but what we need to remember is if we got rid of these modulus signs, you technically just have to think about plus and minus different solutions, and what you can, and you would just get a different arbitrary constant. So you might think that's a bit hand-wavy what I've just said, but it's absolutely fine to basically get rid of the modulus sign at this point. And I wonder if you'd even maybe mark down if you didn't include it. Like sometimes it is important, but here it's okay. We're going to get back to this. So again, we can get rid of it because you can imagine making this thing negative, but we're going to be fixed by this arbitrary constant, and that will just be negative or positive depending on it. It doesn't. We're okay basically to do this. Now we're nearly there. We just have to use p. We know that the curve goes through that point, -4, -3. So I can write down that -3 is equal to k times, and then it's going to be -4 plus 2, which is -2 squared, which is 4. And then x plus 1 is going to be -4 plus 1, that's -3. K is going to equal -3 times -3, 9 over 4. And finally, y will equal 9 x plus 2 squared all over 4. times x plus 1.